Well, good morning, all. And my name is Wayne Fagan. I'm chair of D. Howard International Education Foundation. Welcome to this program, which is part of a series of virtual presentations that are presented by D. Howard International, our other stakeholders, and our partner in these virtual presentations, the University of Texas at San Antonio, Classic College of Engineering and Integrated Design. And just to say a big hello to all the participants on this call, we have Jill Ford from UTSA who will speak in a moment, and Carlos Velez of UTSA who will be the moderator. And our special guests are our students from Stapleton Elementary in Stapleton, Alabama. They're great partners of this program, and we're delighted to see them again and have them back. And then we have the Aerospace Corporation, which is a tremendous collaborating organization with this program, and our special guest speaker, Dr. Larry DeLucas, who will allow Aerospace Corporation to introduce Dr. DeLucas in a moment. But we'll start off with Jill Ford from UTSA, and then Jill, if you turn it over to Aerospace Corporation, and then work it out with as far as Carlos and Dr. DeLucas. And with that, I'll leave you to it. Have a wonderful morning. I know it's going to be a terrific presentation, and enjoy. Lots of questions from the students. We're counting on that in the second half of the show. All right. Thank you all and have fun.
Thank you so much, Wayne. And yes, hi everyone. I'm Jill Ford, the Assistant Dean for Student Success here at the Classic College of Engineering and Integrated Design here at University of Texas at San Antonio. And so we're just so happy to be a partner with the D. Howard International Education Foundation on our Rural STEM initiative. And so just so happy. I want to say a big hello to all the students there at Stapleton Elementary. We're so excited to see all of you. And a big thank you to the Aerospace Corporation and Dr. DeLucas for being our partner in this initiative. And so with that, I'm going to turn it over to Lauren with the Aerospace Corporation.
Yes, hi, I'm Lauren Gandera with the Aerospace Corporation, and I'm here with Roxanne Vibray, who's also with the Aerospace Corporation. It is our pleasure to be speaking to all the students this morning, and hopefully you will feel inspired to pursue STEM. The Aerospace Corporation, we're a federally funded research and development center, and we are so excited to be here with our special guest, Larry DeLucas. He is a scientist, astronaut, and athlete, and I think you'll be really excited to hear from him today. But before we get started, I'm going to pass it off to Carlos to finish up some last mentions before it's officially Larry's time to talk. Thank you.
Yep. So, just for the audience's note, we'll do this presentation. We're going to go until right around just like 5 till 10, or 5 till the hour. I don't know if you're in a different time zone. I think it's a little different for you all. And following that, then we'll have time for questions. So I want you during the presentation to think if you have any questions, maybe note them down or keep them in your mind. So that way at the end of the presentation, you'll have some time to ask those yourselves to the presenter. And from there, we can just go ahead and get started. Dr. DeLucas, the floor is yours.
All right, Carlos, thank you very much. Okay, students, so I'm going to start with kind of just giving you the history how I got interested in space and NASA, and then we'll go from there to what it was like as I trained to fly on STS-50. So being selected, well, I was a payload specialist. So before joining NASA, I was a professor at a university, and I had to first be nominated. There were about 50 or 60 people nominated for the spot that I was vying for. And then they narrowed it to 12 people. My background, you can see here, I had 5. You don't need this to be an astronaut, but I had 5 college degrees. I started in chemistry, then got a Master of Science in Chemistry, got my PhD in biochemistry using a special field called X-ray crystallography, and I'll tell you a little bit about that. And so crystallography, what you all know what crystals are. So we grow crystals of proteins in your body, bacteria, viruses, and then we expose them to an X-ray beam. We actually have a machine to do that right in our lab at the university, but the place where we usually go is I used to in the beginning go all the way to Daresbury, England, where they had a synchrotron. Now we have several in the United States, and I typically would go to Chicago, where there was a synchrotron at Argonne National Lab. But anyway, what the synchrotron is there's a takes up about a city block, and it's in a circle, and in that circle there's a beam of electrons flying around, and with magnets you wiggle those electrons, and when you do, it imparts a radiation from there, and the radiation is kind of channeled down a beam, and you expose your crystal to that one single crystal. And when you do, you get a pattern of little dots or peaks, as we call it. Some are darker than others. They're all in different locations. But mathematically, where they are, how dark they are, allows us to determine the molecule that's inside that crystal. You know, a crystal is usually hundreds of thousands of copies of the molecules, all arranged in a perfect kind of order in 3 dimensions, like a row of bricks on your wall, but in 3 dimensions. But from that, mathematically, you can see on the lower left, we end up getting the structure of the protein. We know where every atom is in that protein within sometimes thousands of an angstrom. So it's very precise. And today, why do we do this? Well, if you know what that molecule looks like, it helps, how it's arranged. It helps you understand how it works in our body. But more importantly, all diseases pretty much are based on proteins in your body that either aren't working right or causing harm, proteins that, end up replicating and making, say, a bacteria that gives you a cold and so forth. And so we can now, from that structure, design a drug, a smaller molecule, it's about the size of 5 of those little atoms you see, that goes in there and blocks the protein and maybe stops it from causing cancer or some other disease. And so it's called structure-based drug design. And today, all pharmaceutical companies do this, universities do this. The university that I was at is still doing it, and we spun out our own pharmaceutical company when we determined the structure of a protein, very important in a devastating cancer. And today, there's a drug that's being used to help people with that cancer. So that's the process. But you can't do any of this if you don't have a high quality crystal. If those molecules that form the crystal aren't arranged very, perfectly, like that row of bricks on the wall, but in 3 dimensions, you won't be able to get good data, and you won't be able to determine the structure. So long time back in 1985, I guess it was, a presentation was made at Marshall Space Flight Center, and this scientist showed on the left a crystal growing on Earth, and that's that. See if my little marker will work here. That's this right here, and the plume coming off of it is lighter molecules floating to the surface as the crystal grows. Well, because they're floating up, and when they hit the top, they come flying back down. If you could see a video of this, and he showed that, it was pretty amazing. Molecules that come in to get perfectly aligned to form that crystal are not perfectly aligned because it's happening so fast. And so when you do it in space, and he did this not with proteins, but with a small molecule like table salt. But when you do it in space, there's the top of the crystal. There is no plume going up because there are no lighter, heavier molecules. So now you use a technique called interferometry, and it just shows density differences around the surface of the crystal. But now the only thing that gets molecules to form the crystal, all molecules are vibrating, and they randomly, vibrate, bump into each other, and make their way to the crystal. But it's orders of magnitude slower than when you grow a crystal on Earth. And as a result, the molecule has time to get perfectly aligned before it gets trapped in a misalignment by another molecule coming in. So when I saw this, I said, wow, he did it with, small molecules, but the same process would be true with proteins. So I designed hardware, and you see it up here, where the protein would be in a syringe, because on launch, we don't want that drop to splatter everywhere, right? And so we can plug it. When you get up there, you turn a crank, and then you don't see it here, but there'd be another crank on this side and extrude a drop that would hang from the tip of that syringe to grow the crystal. So that's what I designed. And from the time I heard that presentation, we built that hardware in a month. And 3 months after that presentation, it flew. You could never fly that quickly today. There's so many other documents and safety protocols you have to go through. But this was back in 1985. So it flew on the space shuttle. And so when I saw that first launch, it just, was so dramatic. And if you have an experiment on the shuttle, you get to watch it, closer than anybody. You're about two miles away. The ground was vibrating, and I was so moved by that. I just said, somehow I want to fly one day in space. And so I tried and kept doing experiments on many shuttle flights, publishing my results. I built up a reputation, and eventually I got selected as a payload specialist. So that process, that selection process, they narrowed it to 12 people. We went and took a 3-day physical. 1 or 2 people failed the physical, but the rest of us then, we took kind of an oral exam in front of all the scientists that would have experiments on the flight that I would hope to fly on. There were 31 different experiments, so all those scientists could ask us questions. They narrowed from the 10 or so of us that were left to 2 people. And then myself and one other person competed for the next year. What did we do that next year? We went to all those universities that had those experiments. The professors were, that have us sit in a classroom just like you're doing now, and they teach us about the theory of their experiments. So we had to learn something I never had, with all my college degrees, all about combustion science, fluid dynamics, all different projects that involve fluid dynamics. Not just my area, protein crystals, but zeolite crystals. They're used as one of the last steps to purify gasoline. And then, of course, semiconductor crystals, totally different process. So I learned all the theory for all these kinds of experiments. Also, I think I still am the only medical eye doctor to ever fly in space, because that was another one of my degrees. And so NASA built special hardware once I was selected, so that, I could give full eye exams while I was up in space. And then for, kindergarten, first graders, maybe, we also had some fun experiments to show how ants without gravity would make homes up in space. Okay, so at the end of that first year, I went back before those 31 scientists, and now my final exam, since now I'm supposed to know all the theory and everything about their experiments, mine lasted about 4 hours, and the person I competed with the same. And at the end, they vote. Person with the most votes gets to fly. The other person has to keep training because he's the backup in case I get hurt while we're up in space. So now the second year I got selected. Okay, I was chosen to fly. We moved to Houston. So I had 3 children. So my family, we all moved to Houston. NASA let me pick out a nice, not exorbitant, but a nice home to live in while I was there. And now I'm learning all about the space shuttle, all about the rocket engines and so forth. And so, back then, the space shuttle, the mainframe computers that operate that shuttle are 1960 technology. We even had what's called a PDP-8 computer, where you had to put a ticker tape into it to get it to work. I often asked, why don't they upgrade the computers? And I guess it was a combination of the cost and, they work. And so they didn't want to change anything. I had to learn how we were going to fly around Earth, the whole orbital flight that we would be taking. There are many processes where if there's an emergency, we had to learn how to rappel off the top of the shuttle. Way up here on the top, there's two windows, and you can explode those off the shuttle. If we land and let's say it was on fire, we can kind of pull ourselves up the top and rappel down the side of the shuttle. So I had to do some rappelling. We had to learn what medicine we can tolerate because many astronauts do get sick when they're in space. We learn about fire safety. Depending on the type of fire, you put it out with maybe not water, but some other chemical to extinguish the fire. And then every once in a while, we go back to Marshall Space Flight Center to kind of rehearse the science again. There's also a process where we're up on the launch pad ready to go. And let's say, the shuttle's going to explode or there's toxic fumes. So there's a zip line we can go down. And when you hit the sand pit down here, what if there's an explosion? We could still be hurt by shrapnel. So we actually get in a US tank and drive it away. That was a lot of fun for me. We go to Brooks Air Force Base and we get in a centrifuge because they want you to make sure that we can take the G-force on launch. It's not that bad with the shuttle. It's about 3.2 Gs, but it is sustained for about 5 minutes. So we do that. And then the fellow running it said to me on a little microphone in my ear, "You want to see how tough you are?" And of course, I'm very competitive. And I said, "Yes." And so he goes faster and faster. And I actually got up to 8.3 Gs before I started to pass out. A lot of fun. That's me practicing the bailout procedure. We practice what if we launch, but we can't get to space and we have to now bail out of the shuttle. So we're wearing these pressurized suits and there's a hatch on the side of the shuttle. We can explode the hatch off, jump out and parachute into the water in the ocean. This is me. Once you hit the water, I'm practicing first in a swimming pool. You blow up this little raft that's in my backpack. And in the real process, once I did it in a swimming pool, we actually parasail. We go up to about 500 feet and then we release the line and then parachute into the ocean. Can't see your crew. And I stayed out there about 12 hours in this little raft here. A lot of fun, right? Then I vector a plane to come find me. You can't see anybody else. You're all by yourself. You can't see land. You're way out in the Atlantic. And then once the plane spots me, a helicopter comes, lowers a big kind of sinker. I grab it and it pulls me up in, and then I'm back to safety. We also practice kind of simulated not having gravity by getting in a large plane. It's called a KC-135. It goes up to about 40,000 feet, and then they just turn the engines down, and now it's falling at the rate that gravity pulls you. As a result, inside the plane, there's no gravity. And so that's me wasting taxpayer money, having a good time. But most of the time, I was strapped to the side here, practicing, how will a droplet hang on the tip of that syringe? How will a G-force of any kind, will it make that drop fly off the tip of the syringe? So it's a great vehicle to kind of make sure your science is really going to work when you get in a no gravity situation. That is my launch right there. And then, of course, I always show this image, that's me, believe it or not, when I still had black hair. I was 42 years old, and that is the Columbia that I flew on. And that's the crew that I flew with right there. The commander is in the middle, Dick Richards, and the pilot, who was a rookie, is right here, Ken Bowersox. He then later became the head of the whole astronaut corps. So when you go to space without gravity, of course, that's the way a candle burns on Earth. As it burns, warm air rises because of gravity. Cool air comes from below, pushes that candle kind of into a point. It's yellow because it's getting a lot of oxygen. When you burn a candle in space, there is no warm air rising, so it burns as a blue ball. And again, how does it keep burning? It needs oxygen, right? As it uses up the oxygen near the wick, it takes longer and longer for oxygen molecules, which are vibrating, to bounce around and make their way to the wick. In 40 seconds, that hot blue flame extinguished without gravity. And this is just an experiment again that we did for young children. So in space, just some fun slides. How do you take a bath? Well, even on the space station, Carl Mead called them Mad. Everyone had a nickname in space. He was Mad Dog Mead. You can squirt no rinse shampoo on your head. You lather up and just dry off with a towel. Because we stayed up 14 days, it was the first extended duration mission. We had these little kind of boxes we could sleep in and close it to give us some privacy. And I would get in there and listen to music while I was in there. And the food comes in trays like this. That's chicken soup. You can dip your spoon in, pull it out, and you got a bubble of chicken soup on your spoon. Why doesn't the liquid go over the edge? Because right here, it's hard to see, but there's a sharp 90-degree corner. It's called a pinning edge. If you have that, the liquid will come up to it. As long as it's not rounded, it won't flow over it and spill out. I'll never forget the first thing I did when I got up there is I went for butterscotch pudding, which came in these pop-top cans. And I forgot, NASA said, do things slowly. Well, I popped the top and my butterscotch flew out of the can and splattered all over the wall of the shuttle. So everyone wants to know, how do you go to the bathroom? Well, you sit on this commode, you see these blue things, they're spring loaded. You lift them up, twist them over your legs, and they push you down into the commode here. So you make a good seal around that. Then you take this ball and push it forward. When you do, it turns a vacuum on right through the commode. And that's all I'm going to say about that. Just a pretty few slides. These are, we took our photographs with film back then. So you're looking at a sandstorm, and I'm sorry, it's kind of damaged from old age, but coming off the coast of Saudi Arabia. 14 days later, you could see the trail of that sandstorm all the way across the Atlantic over Cuba. And we were supposed to come back in 13 days, but because of Hurricane Darby, right over Edwards Air Force Base in California, we had to stay up an extra day. I say we had to. All the science was put away. Now we could have some fun. That's when I spent a lot of time taking photographs, looking out the window. Also, I love sports and I love basketball. So NASA let me bring a little Nerf basketball and a plastic goal. And I think I beat Michael Jordan's hang time floating through the air. I did a flip, bounced off some walls, and then slam dunked it through the rim. So I had a lot of fun. The last day, I fell asleep. I wasn't getting a lot of sleep while I was up there each day. And I was in the middeck. And in the middeck, there's a cabin fan that kind of cleans the whole shuttle. And it blew me while I was sleeping into the airlock right there where we keep all the dirty laundry. And it was about 2 hours later, everyone said, "Where's Larry?" And they went looking for me. Unfortunately, that's the way they found me, in the airlock. And then finally, we did have to not land in California because of the weather, and we ended up landing in Florida. So I'm going to stop there. I think we got plenty of time for some questions. And I'm going to turn off the screen share so I can see people. There we go.
Anybody have a question? Oh, wait, I'll come to you. Anybody have a question? All right, Kenzie?
Would you go to the moon if you could?
Would I go to the moon if I
Would
could?
you go to the moon if you could?
Yes, absolutely. I would love to do that. Once we figure out a lot of the issues in deep space, there are many that I could talk about. I'd love to be a person going to Mars.
Anybody else?
All right, Cole.
We have a question.
Releasing gas in space, like from how you move in space, why does that move you exactly?
So even though there's no weight, every action will have a reaction. And so you do have momentum. And so the thrust does push you, even though, if you talk out in space, if you could, because we're inside a suit, but if you talk out in deep space, of course, sound won't travel without any air in a vacuum.
We have a question. Hugh right here wants to know, what is the hardest part of training?
Well, I'm embarrassed to tell them this, but for me, it depends on each person what they'll tell you. But for me, it was the parasailing and parachuting into the ocean, because believe it or not, the reason I'm embarrassed is really I'm afraid of high heights. So I can get in a rocket or a plane, but I don't like to get on the edge of a cliff, for example. So I did it, but that was pretty scary for me doing that.
And then we can take one from Kayla or Miss Kayla Emerson.
Thank you. This is Ian. He's got a question.
Is going to space scary?
You know, you do a lot of training and you think about all the things that could go wrong, and then you have scenarios where you practice. If this happens, how do we avoid it? You know, how do we save ourselves if there were a fire or something like that? And so in the end, you're pretty confident that whatever goes wrong, you're ready for it. You know, for example, I remember on launch, I'm looking at 3 cue cards that tell me what I do if we have to get out of the shuttle as we're higher and higher, you know, leaving Earth. Because if you get pretty high, you know, you don't have long before you'll pass out without breathing pure oxygen. That's why we wear that sealed spacesuit and the visor's all sealed and so forth. But if you didn't have that, you know, how long can I stay cognitive? You know, my brain's still working, I'm still awake, I'm not passing out with very little oxygen. So NASA actually has a chamber that you get in, and they lower the amount of oxygen in that chamber, and they show you what it would be like without that helmet sealed at, say, 15,000 feet, 25,000 feet, and then 40,000 feet. And I can tell you, the way they determine how well you're doing, they asked me to count backwards from 100 when we were at 25,000 feet. And so, you know, when you don't have much oxygen, you kind of get silly. And so I was there and I said 100, 99, 98. And then pretty soon, all of a sudden I go 64, 33. And I got a big smile on my face. I was just losing it. And they know, okay, he's not going to be awake much longer. And so they stop it at that point. There's a lot of fun doing that with everybody.
Nice. And then, yeah, one thing that can help us make this a little easier is maybe if you have the students come up to the front like we have now, and we'll pick the students that are ready to ask questions. So yeah, Miss Walden, your class here, you're good to go.
Okay.
What color on the crystal equals H2O2?
So you're talking about the crystal having a color?
No, like on the machine, it showed a dot, and the darker the color, the color determines what.
Oh. So usually depending on the actual atom, we color them differently. So oxygen is usually red. Carbon is usually green. And nitrogen sometimes is blue. That's pretty much the standard. We do that so that when you look at something, you can see where oxygen molecules are and hydrogens and so forth, because that kind of gives you a clue where something, especially in a place where you want a drug to bind, if there's an oxygen molecule there, you know, which is more of a negative charge, you want your drug maybe to have a hydrogen to make a hydrogen bond to it so your drug will stick in that place.
Do we have anybody from Miss Elliott or Winstead's class? Was that?
Yeah, here's the best thing about your job.
Let them in first.
The neatest thing about my job.
I
Well,
forgot I was
you know,
to say.
Was that the question? Yeah. So I think it's the excitement of discovering something that no one had done before. I remember one project that we were trying to crystallize that was very important for developing a drug for diabetes. And after 1 year, we couldn't get great crystals. And pretty soon I was worried, am I going to have to quit after all this work? And then my technician came and knocked on my door. She opened the door and she was jumping up and down. She said, come in the cold room, because that's where we grew the crystals, in this cold room. It was at 4 degrees centigrade. I ran in there, looked in the microscope, and we had it after 1 year. I could not go to sleep that night. And, with the space experiments, when we bring the crystals back and find crystals that were much better than we ever saw before, we used to record the reaction of scientists. And it was just, it was just amazing to hear what they said, because some of them worked years on a project and couldn't get the kind of results we got with crystals coming back from the space shuttle.
Thank you.
Thank you.
Now we'll do Miss Winstead. Yeah, very good.
Okay, Chaplain.
What did space look like?
So that's a great question. I'm also an amateur astronomer. I have 5 telescopes right now, and I can go outside tonight and show you every constellation and pick out all the planets that you can see and so forth. I got up in space and I couldn't find the Big Dipper. It's everywhere I looked. There were just thousands of stars, and I just was totally lost in space. It was so confusing for me. And a funny story, I didn't realize it, but when we go on the space station or the shuttle, you think we're far, far away. We're 250 miles above Earth, right? So the Earth is this huge ball. The moon is 240,000 miles away, and it's an optical illusion. It made the moon, compared to the big ball of the Earth, the moon looked like a little tiny planet. It looked small. It didn't look the way it looks here when you look at it. From here, if the moon's close to the horizon, it looks bigger than when it's up high. Well, it's dramatically shown when you go to space, that big ball of the Earth and the moon. It makes it, I thought it was a planet when I first looked at it.
And then, yeah, Miss Emerson's class, 4th grade.
I know that the water in space would probably like get into stuff, mess it up. But how would you just lather soap in your hair and then wipe it off with a towel?
Yeah, it's kind of a dry rinse, so it's not very watery, and so it's real easy to dry off. When I finished my mission a year later, I became the chief scientist for the International Space Station. And at that time, we were building the space station, and we thought, let's build a shower, right? And so the design, you get in this, it looks like a shower. You get in this kind of shower and you turn on the water. When the water hits you, it's not going to fall to the floor. There's no gravity. So now you get this bubble of water, because in space, the attraction of a liquid for a surface, it's called surface tension, dominates everything. So as you have the water hitting you, it's pretty soon going to be a bubble over your face, your mouth, your nose, and you soap up. So now you got a soapy bubble all over you. Now, how do you get it off? Well, you could be like a dog, maybe, and shake, and some of it would fly off. But what we said is we'll have a vacuum cleaner and we'll have to suck the water off. That's maybe why it never flew in space. So today, even on the space station, they do what's called a dry shower with this. It's a kind of a foamy soap that you squirt on yourself and just dry it off.
That's crazy. All right, and then we'll do Miss Walden's class. Miss Walden, yeah.
Yes. Maddie?
Who built the first ever space shuttle?
Who built the first ever space shuttle?
Who built it? Oh, it was a combination, not just NASA, but many aerospace companies were all involved. Some of the NASA centers, the Jet Propulsion Lab, Marshall Space Flight Center, was responsible for a lot of the rocket parts. So it's always, probably, I'm guessing, but 50 to 100 different companies helping build small parts, and then it all gets put together, usually at NASA.
Nice. And then we'll do Miss Elliott. Yeah.
Right, Bentley.
wasn't it hard because the food would just fly around?
Not sure I heard that.
Wasn't it hard because to eat because wouldn't the food fly around?
Oh, so when you know dip a spoon in the food, as long as it's got a little bit of liquid, it sticks to the spoon against because the traction of a liquid for a surface. So you know, as long as you do it, you don't go quickly like I did with that pop top can. You know, it'll stay stuck to the spoon, and then you eat. One of the harder things was drinking liquid back then because it came in a kind of a bag you could squeeze. You put your straw in this little hole in the top. Well, as you start drinking the liquid, the rest of the liquid sticks to the wall. So now in the middle of the bag is just a big air gap. And so I had to point my straw toward the wall and then squeeze the bag to get liquid where the straw was pointed to get the rest of my lemonade or whatever I was drinking. So it's kind of a terrible way to have to drink liquid, but that's what we had to do.
I'll say thank you.
Thank you.
And then Miss Winstead. Okay, Winstead.
How does the toilet work?
Said, how did the toilet work? How does the toilet work?
How does the toilet work? Remember, you sit on that commode, and then again, it's like a vacuum. When you push the ball forward, it just sucks everything down into the toilet. You have to use your imagination for the rest.
And then now you, Miss Emerson.
Oh, sorry.
Do you like being an astronaut? And if so, why?
I loved it. It was so exciting to learn all these, you know, kind of not just the science, which I love more than anything, but also to do all the physical training. I guess because, you know, when I was young, I was on the basketball team in high school and the baseball team. I've always loved, you know, some physical activity, and NASA combines all that when you're exploring. And so, you know, just to be in good shape, we would run 6.4 miles every day down in Houston. That's the loop around Johnson Space Center. And so I was in great shape at age 42. And so I guess it's a combination of doing physical things along with learning great science and exploring. It's just fun to explore and discover something new.
Yep. Miss Walden.
What is a payload specialist?
Great question.
And they also,
So,
piggybacking on that question, they're curious how much would a professional, you know, like that make, like money?
yeah, yeah, good question. So back then, okay, you know, the typical, so let me describe the term. Payload specialist is someone that doesn't spend his whole life flying. So again, I was a professor. There are some payload specialists that flew 5 flights. After my flight, I became chief scientist of the space station. So I spent 2 years up in Washington at NASA headquarters. And that was the end of my flying. I didn't do it again. I could have tried, but I didn't. I wanted to do science and put my experiments up in space, but not me go with them. Okay. A mission specialist is someone is their career is a NASA astronaut, and many of them are also pilots, but they can't fly the space shuttle, but they are, you know, they can fly a commercial jet, for example. And then from a mission specialist, you have the pilot, and then finally the commander. The commander usually has flown one time as a pilot before they become commander, and it's really the commander that lands the space shuttle. A payload specialist is typically someone that's not a career astronaut. They come usually from other science universities or some science program. And then because of their experiments, they're needed to fly on the shuttle because they're the expert. I was an expert in crystallography, in growing crystals. And when I was up there, you know, I had oh, I don't know, 30 some proteins that I was growing crystals of for people all over the United States for other professors. So I was taking their protein, growing crystals for them. When we got back to Earth, I gave them back all those crystals, and then they went and used them to determine structures. So a payload specialist is usually a scientist, some expert with a particular type of science that you're going to do on the shuttle.
You know what the pay was like? Like around or
Oh,
general
the
pay?
pay, yeah, the
Yeah.
payment, excuse me. Yeah. If you don't have flight pay, which is what the commander and the pilot would have, then a typical astronaut is making today, I think, around $130,000 per year. If you get that extra flight pay, it goes up maybe another $15,000, $20,000 more than that.
And then yeah, Miss Elliott's class.
Is it true?
Mrs. Lee.
Is it true that your NASA is decommissioning and deorbiting the International Space Station?
Yes, it is true. And right now, it would be totally kind of left abandoned around 2030. So, what's not too many years away, about another 5, 6 years. And what they would do is let it burn up into the ocean. The space station can actually, like just like a space shuttle, you can fire what's called vernier rockets on it and have it, deorbit wherever you want. So it won't land on land and hurt anybody, but it would land in the middle of the ocean, and most of it would get burned up coming in. Unless some company wanted to take it over, that's a huge expense. I don't think that'll probably happen, but if a company did, then it might stay up longer.
And then yeah, Miss Winstead.
What is the hardest part about being an astronaut?
The hardest part of being an astronaut, for I think for most, when you're getting ready for a flight, for me as a scientist, I didn't want some person that waited 10 years to fly their experiment in space to find that I did something wrong and it ended up not giving them the results they needed. And so for me, the hardest part was to make sure, first on Earth in the training, that I was absolutely the expert, like that scientist, and knew that I would do the experiment just the way he wanted. Then, when I got up in space, I made sure if I saw something a little different before I would go and press a button or add some liquid, that I would check with that scientist to make sure they wanted me to do it, because I didn't want to have to come back and they were all disappointed. So I felt a lot of pressure as I did the experiments for other scientists to make sure that I did it correctly. And the whole time you're doing this, there's a camera watching you. So again, you want to make sure you know exactly that you're going to do it right.
And then yeah, Miss Emerson.
All right. So my question is, do you have any fun in the anti-gravity?
What about anti-gravity?
Do you have any fun in the anti-gravity?
Oh, yeah. When on our crew, there were 7 of us, and 5 people the first couple days were sick. I don't know why I don't get sick in space. And so as soon as I got up there, I started eating. And they told me I was the only astronaut in something like 12 missions. After I came back, I had actually gained 3 pounds. Most astronauts lose a little bit of weight. But they had these Dolly Madison rolls on my flight, about 200 of them. And I think I ate half of them. So maybe that's why I gained weight, because I really like the Dolly Madison rolls. But for me, it just was, a lot of fun, because I didn't get sick at all. And I just enjoyed every minute that I was up there.
And then yep, Miss Walden's class. Oh, yeah.
Okay. So we're not ready for another
Okay.
question.
Yeah, we'll loop back around. No problem. And then from here we're into where I got lost. Oh yeah, Miss Elliott.
My name is Joshua, and my question is, what's the worst scenario that could happen on a mission?
It's a little hard to hear. Yeah, you might need to repeat that. Just a little further away.
What's the worst thing that could happen on a mission?
The worst
Ooh.
thing to happen?
Yes.
Yeah, we actually had a fire, and it was in a ultrasound machine because I was doing a experiment called lower body negative pressure. They take and I get in a bag and it seals around my waist right here, and then it sucks a vacuum to pull the blood, because when you go to space, your blood shifts upward and it pulls it down into my legs just like gravity on Earth does. And so I was in that bag and my head was underneath the machine. So I'm all strapped in. I can't move. And then another crew member is looking at my heart with an ultrasound machine and looking at how well it's doing as the blood gets sucked down to my leg. Well, while they were doing that, I started smelling smoke. And I said, turn it off. Something's on fire. And they couldn't smell it because they were up further away. And then all of a sudden, a big puff of smoke started coming out of the machine. And they quickly turned it off. Had they not done that, and that thing had burst into flames, probably would have burned my face. But the other thing is, there's little sensors in the shuttle. And if the particulate, the little pieces of smoke, reaches a certain level, then automatically you fire the halon bulbs. That's like a fire extinguisher. And if you do that, the whole back of all the instruments gets soaked with all the halon. And so as a result, we would have had to come home and it would have ended the mission. But fortunately, the other person turned the machine off and the particulate didn't get high enough to make the alarm go off. So we were able to stay flying. But we did shut that one off and we never could use it again for the rest of the mission.
Thank you.
Miss Winstead.
No. Okay. Kanan, come here. Sorry, give me 1 second. She got shy. Okay. Just 1 second.
How does it feel like whenever you get back to Earth?
Another great question. I got after 2 weeks, I was pretty used to no gravity, right? And so in space, I could brush my teeth and then just let go of the toothbrush, let go of the toothpaste, and it just stayed right there. I got home that night and I brushed my teeth and I dropped the toothbrush. It just fell on the floor because I was still thinking I was in space. Your muscles are kind of weak, and my sense of balance is not right. And so they test that, to make sure I get back to normal. And because my balance, if I turned my head, things were spinning around me like that. If I looked down, it was kind of flipping like that, up and down. And so NASA would not let me drive my car for 2 weeks until after my mission. 2 weeks later, then I was allowed to drive, because that's when it's called your vestibular system. That's your balance system. That's when it got back to normal.
And then you, Miss Emerson.
What was your favorite meal and drink when you were in space?
Yeah, this is another funny story, because on Earth, this was my first flight, my only flight, right? And on Earth, you get to try all the food. Well, I like the orange drink. And so the way we tell my food from another person's is everyone has a dot with a stick-on dot. It's a little paper stick-on dot. And my color was brown. And I put brown on all the orange drink for 14 days that I was in space. Well, someone that had flown before on my crew said, Larry, you may not like the orange when you get up there because your sense of taste changes when you get in space. And I thought, no, I don't like anything else. I'm taking the orange. Well, I got up there and the orange had no taste at all. Okay. And so, the only drink that I could really tell it had a taste was the lemonade because it was tart. Why is that? Well, when you go to space, your fluid kind of shifts upward. You get a puffy face and it clogs your sinuses, so you can't smell very well. And if you can't smell, then you can't really tell something, that you're eating, right? But the lemonade, because it was kind of tart, it gave me a sensation. So I really liked the lemonade, and we all started stealing each other's food. So I was stealing lemonade when I could get away with it from someone else, and I gave them my orange drink in trade. In terms of the solid food, I on Earth, I hate shrimp cocktail. I hate shrimp, but in space, that was very kind of tart for me, and I liked it. And so I started eating shrimp cocktails up in space, whereas on Earth, you'll never catch me eating it.
I love shrimp cocktails. That's crazy. All right, and so we're gonna just do one more round of questions. So this will be our last ones from each of the classes. So we'll go over to Miss Walden's class.
What would happen if the little backpack, parachute, or raft flipped over?
If what flipped over during a parachute?
The backpack when you said you fell into the water.
Oh, well, the backpack, it's hooked to my back, right? And so you parachute, the parachute is a separate pack. You pull one cord and it releases the parachute. The backpack isn't connected to that. So now the parachute goes up. When you hit the water, you release the parachute, and then you reach in your backpack in the back, pull out that raft, and then you can blow it up with your mouth, or there's a little button you can push, and a CO2 cartridge will automatically blow it up.
And then I always get lost when you Miss Elliott's class.
My name is Cole. My question is, how thick is the material on a spacecraft?
How big is
How
what?
thick is the material? Like, I guess like the outside of the spacecraft. Is that what you're asking?
Yeah, how thick is the
Yeah.
metal? Like how thick, like how big, how much, like how much
Yeah.
metal, like how thick is the wall basically from you in space?
The wall?
Mhm.
You mean
Yeah, of this like space shuttle. Like so,
the
like
space
from the
shuttle
inside to
wall?
the outside. Yeah.
Yeah. It's about like that, but the outside, if you ever look at the way the space shuttle was designed, the bottom of it is black, and it's because it's carbon-based tiles that will withstand the heat. The upper part that's white, that you can stick your finger and kind of scratch it and probably scratch a good chunk of it right out with your fingernail. So it's a soft kind of material. But those tiles are about almost an inch thick. And then there's a layer under that of the structure. The structure of the shuttle is aluminum. Okay. And then on the inside, it's just a very thin kind of what you'd have in, it's not plaster, but something like you'd have in your house, very thin wall.
All right, thank you very much.
Yeah.
And then Miss Winston.
So can you like grab a star or something? Grab a star.
No, we're too far away. I mean, we're only 250 miles above the Earth. So, those stars are millions of miles away. So, is that what the question was? I think it was.
Yeah.
Yeah.
Mhm. And then Miss Emerson.
This was the last question for our group.
Why haven't we been back to the moon? And how do you burp in space? Because you need oxygen to burp.
So in the shuttle, we're breathing oxygen just like here. It's actually not pure oxygen. It's 21% oxygen, just like we have on Earth. So it's air. And so, no problem breathing in and out without a mask on or anything like that. So, if you burped hard enough, and you're floating, it probably would propel you backwards because again, that force of pushing the air out would push you backwards because you have no weight.
Do you like have more or less burps, or is it like the same amount as you would here?
More or less burps.
Yeah, like are you more burpy there, less burpy?
Yeah, I don't think there was much of a problem with burping. The
Okay.
biggest problem when you first get to space is your intestinal area shuts down, and it takes a while to learn to use your muscles to go to the bathroom.
Mhm. And then the second part of that question was about like going back to the moon or like going to the moon again.
Say it again.
Yes.
Why haven't we been back to the moon?
Why haven't we? Probably a combination of the cost, and people thought, why? We went there 12 times, and why do we need to, or we put 12 men on the moon and returned them. Why do we need to go back? Well, today I can tell you there's some good reasons to go back. One is the moon is full of helium-3. With helium-3, you can do the safest way to create energy is nuclear fusion, but with helium-3, there's absolutely no damage, no danger from radiation. Another reason is you hear today about rare earth metals. The moon has a lot of that. Now, bringing it back and the weight and the cost is one reason it hasn't been pursued, but now there's a lot of interest, especially by companies, to go to the moon for those reasons. And that's why China wants to go. The best place to go would probably be the South Pole of the moon, where we believe there's quite a bit of water. Because if you're going to go there and you're going to set up a base to, mine for helium-3 or even rare earth metals, you need water to sustain life. And so that's probably the best place. And that's why, there's a race to maybe get back to the moon today.
Awesome. So great questions from the students of the class. Thank you so
They
much
were.
for asking all of these questions.
Yeah.
So to close out, I usually like to do a couple of things, which is one, we'll have you give some like final like advice or words to the students. But any of the aerospace folks, would y'all like to say anything to like? I know sometimes y'all like to also shout out some things, not to put you on the spot or anything.
Yeah, I'll just step in my advice, and I always tell students, they ask me, what do you need to do to become an astronaut or become a scientist? And my answer is read. Read as many different types of information as you can, because having a good background in many areas will let you, as you get older, kind of figure out what it is you want to do. And you want to pursue something that, for me, getting up and going to the lab and growing crystals and determining structures was as much fun as playing basketball. It was like, it wasn't a job. It was fun to do it. That's what you want. And to prepare for that, you need to have a broad background. And, if you're just really good with books, that's not enough. Also, be active. NASA looks for people that have either been in the Boy Scouts or does camping or likes to go scuba diving. They want people that can explore also.
Awesome. Yeah. Did you want to say something? Aerospace.
Yeah. Oh yeah, nothing
Yeah.
else from us. Thank you for having us. We appreciate it. We appreciate you guys having time for us this morning. And thank you to Dr. Larry DeLucas.
Yep. You're welcome.
Yes.
All right.
All right. And yeah, with that, we'll go ahead and close out. Thank you to all the students for being here. Thanks for your time and attention for this presentation. And thanks for all the questions.
Great questions. All right. Bye-bye.
Bye,
Bye, everyone.
everybody.
Thank you, Dr. DeLucas.